ShellBytes here. Today we're going to be looking at the instruction set for our build your own Minecraft computer. So none of these instructions are set in stone. I just realised we didn't have an instruction set yet, so I went and made one. These are sort of based off the x86 instructions and some other videos that I've been watching. So I have got a sort of user-friendly opcode to tell you what all of these things do. So obviously when you run them in the computer, you're going to have a binary value that will be executed, but there's obviously like parameters that we're going to need to pass in. So basically the way it works is we type in our opcode. So say if we wanted to, for example, store an immediate value or a constant into register A, that's IM_A, so that's 0, so the instruction that we'd actually pass to our computer is 0, 0, space, and then say we wanted to store the value, I don't know, 33, let's say. So that's 0001, 0001. I believe that's 33 in binary, but that would be the instruction that we pass to the computer. So that's basically how we handle immediate values. So in our key here, we've got 3 registers that computer operates on. Yeah, quite small, yeah, but 3 is the only amount that we really need. There is also the addition of the carry flag, so that our 8-bit computer can add up to like 32 or 64-bit numbers if we really wanted to. And obviously I've just got this just to show you what it does. It's like the opposite way around. So if I was opposite way around to normal programming languages, so if I was to do A arrow B, that means I'm setting B to whatever value A holds. I think that's just a more intuitive way for some of this. So I'm going to go through each of these in turn and show you what they do. So the first one is the no operation. That's fairly self-explanatory. It does nothing. Then we've got add. Then they will add registers A and B together and store it in O with the carry in the carry flag. We've got subtraction. Shift left basically means that we're going to bitwise take each bit and shift it 1 to the left, and then 1 to the right for shift right. Jump is basically like a go-to statement. You will go to a specific line number, which is the immediate. Then we have the jump if equals. So if register A is equal to register B in every way, then we're going to jump. If they're not equal, then we're going to jump. If they're greater than, we'll jump. If they're less than, we'll jump. So they're all self-explanatory. We then have OR. We're going to take the value of A, bitwise ORed with B, and store that in O. And then we're going to do the same with AND. We've got A, bitwise AND with B, and we're going to store that in O. Then we have NOT, and it will just literally invert every bit and store that in O. We've got NOR and XOR, they all work the same way. Now, with store, I've realised that comment's on the wrong line. With store, we're basically going to take the output and store it in some register somewhere, some sort of memory, and it'll probably be RAM. So basically the way it works is that the immediate value is actually a pointer. It tells us which register or which piece of RAM we're actually going to save it to. So obviously that would just be numerical. It might be like something for across and something for up if we make 2-dimensional storage, which we probably will. So then we've got load A and load B. What they do is they take a value from RAM at the location of the immediate and send that into register A. Then we've got load B, which will send the same thing into register B. Then we've got 2 functions, immediate A and immediate B, which will send an immediate value into A or into B. Now we have this function, clear carry flag, and what that will do is it will basically set the carry flag to nothing, we've got set carry flag, which will set it to 1. Then we've got add with carry, or ADC, and that basically will add A and B with the addition of the carry flag. Then we've got increment and decrement, which will just add and subtract 1. Then we've got wait, which will make the program wait for A seconds. I'm not sure if I'm actually going to include this one because I don't really see where it would be useful, but still, I've got it in there just for the purposes of maybe if you wanted to have some sort of delay. You might just use no operation for that though. Then we've got an end process, and that will basically terminate the whole program. It will just stop it from running. Then we've got BCD, and it will take A, it will take anything in register A, find the packed BCD equivalent and store that in O. Then you've got binary from packed BCD, and what that does is it takes a packed BCD number in A and it will convert that to normal binary and put that in O. Now we have in A and in B, and the user will obviously be able to input something, and the user will have some inputs, and it will store something from those inputs into one of the registers. And then we also have output, which will basically store the value of O into some sort of output that the user has. And finally, we've got load carry flag. This will basically set O to this carry flag, and that means O will either have all of the bits on or all of the bits off. Now these last 6 we might not include. So multiplication and division, they're obviously very difficult to implement. Then we've got these 4 that require a GPU, so that might be quite difficult as well. But anyway, I've included them just because they might be cool. So obviously multiplication and division, they work quite intuitively. Obviously multiplication will only store the first 8 bits because that's the size of register O. In fact, all of the registers are 8 bits apart from obviously the carry flag, which is 1 bit. If it's higher than 8 bits, it will set the carry flag. Then obviously with division, it's only going to do integer division. If it's like, if you do, for example, 8 divided by 3, then that will just give you like 2. Then we've got some stuff for GPU. So we're going to set pixel. So if you imagine our GPU as an array, a 16 by 16 array of pixels, it will be able to take A, which is an 8-bit number, split it up into 2 4-bit numbers, like this. So if we have like that as an example for our contents of A, it will split that into those higher 4 and lower 4, and that will be the x coordinate would be 2 and the y coordinate would be 14. I believe, is that 14? Might be 13. Not quite. Yes, it is 13. So it would be that indexed on the pixel, and it would set it to, if B is 0, then it would set it to off, but if B is anything else, it would just set it to on. Then we're going to do some fill on. We're going to go from pixel A to pixel B. So obviously pixels A and B will, like registers A and B will represent pixels, and they will fill between them, all of them on. And FLO is very similar, except it will fill them to an off state. And then CLS is obviously clear screen. So that wraps up the instruction set that we're going to be creating. So I'll join you in the next video where we're going to be starting to implement the rest of this.